let's say I'm person A here in my ship traveling through the universe at a constant velocity. So that is person A right over there. Let me write it a little bit bigger. So person A. And let's say that I have a friend, person B, and they are in another ship. And in my frame of reference, so this is person B, in my frame of reference, they are traveling, so their velocity vector looks like this. They are traveling at 8/10 of the speed of light, 0.8 c. And so once again, this is all given in A's frame of reference, in my frame of reference. Now the question I have for you is, surely there must be some third party, let's call them C for convenience. Surely there must be some third party or some third party frame of reference, and we could imagine it might be someone in some ship, where their velocity in my frame of reference is in between being stationary and traveling 0.8 times the velocity of light, and even more, from their frame of reference, A and B should be leaving or going outward from them at the same velocity. So what am I talking about? So this is, we're going to, in this column, I'll write the frame of reference. So this first row is A's frame of reference that we just described. And C is going to be going with some velocity V away from A. So some velocity V. We haven't figured it out yet. Now let's think about C's frame of reference. So frame of reference C. So C in C's frame of reference is just going to be stationary. And we want to figure out a V so that A and B are moving away from C at the same velocity. So in this frame of reference, A will look like it's moving to the left with a velocity of negative v, or its magnitude is the same, but just in the other direction. And B will also be moving away with velocity v. So B, right over here, is going to be moving away with velocity v. So this is a really interesting question. Can we figure out what v is going to be? If we were dealing with the Galilean world, you might say, well, v is just going to be halfway in between these two things. If we were just on the highway in a Galilean or Newtonian world, and b is going 80 miles per hour, and a is stationary, well, then if c goes halfway, if c is going 40 miles per hour, then from c's point of view, it looks like a is going backwards at 40 miles per hour, and it would look like b is going forward at 40 miles per hour. But we know by now that we aren't living in a Newtonian or Galilean universe, where we're living in one defined by special relativity. So I encourage you to pause the video and figure out what this in-between frame of reference, what its velocity needs to be relative to A. And I'll give you a hint. It's going to involve the Einstein velocity addition formula. So let's work through this together. So I'm just going to write down the Einstein velocity addition formula. So it tells us that the change in x, change in x prime with respect to t prime is equal to u minus v over 1 minus uv over c squared. Now let's think about how we might apply it. And the trick here is to really think about it from C's frame of reference, So if you think about it from C's frame of reference, you could say that V, right over there, let me do this in a different color. You could say that V is the velocity that A is moving away from C at. So velocity A moving from C. And then you could say that U is the velocity that B is moving from C. Remember, we're dealing in C's frame of reference. So velocity that B moving from C, and actually let me make everything uppercase. This should be uppercase A, and this should be uppercase C. And in that case, what is delta x prime over delta t prime? Well, that would be the velocity that B is moving away from A in A's frame of reference. I know this can get a little confusing, but I really want you to pause it, watch it in slow-mo, really think about what we're doing. I'm kind of starting now. I know I started this video in A's frame of reference, and this is really the trick of the problem, is I'm now shifting over to C's frame of reference. I'm like, okay, V is the velocity A is moving away from C, B is the velocity, or U is the velocity B is moving from C. And in that case, we can view delta x prime over delta t prime as the velocity that B is moving away from A in A's frame of reference. So B moving from A in A's frame of reference. So in A's reference. And both of these are in C's reference. And let me write that down. In C's reference, in C's reference. Really want you to think about this. This is a little confusing, but hopefully this helps you appreciate how this Einstein addition of velocity addition can be valuable. Well, now we can substitute what we know. We know that the velocity B is moving away from A. It is 0.8 c. So we can write 0.8 c is going to be equal to u, the velocity B is moving from C in C's frame of reference. Well, we say that's just going to be v. That's going to be a positive v. So that right over there is going to be a positive v. Let me do that in that same color. It's going to be a positive v. And then from that, we are going to subtract the velocity A is moving from C in C's frame of reference. So A is moving from C with the velocity negative v. I know it's confusing to replace a v with a negative v, but this is a generalized formula, while this is the actual value that we're using in this case. So minus negative v, all of that over 1 minus the velocity of u times the velocity of v. Well, or that's going to be v times negative v, or negative v squared. So I'll just write that as negative v squared over c squared. And just like that, we have set it up so we can solve for v. And the key realization is that we said, okay, there must be some spaceship C that defines a frame of reference where A and B are moving away from it with velocities of equal magnitude. And so we use that information to go into C's frame of reference and use the Einstein velocity addition formula. But instead of knowing what these are and then solving for this, we know what this is, and we're assuming that these two have the same magnitude, and we're able to solve for v. And so let's do that right now. In fact, I will do that in the next video so that we have enough time, and I encourage you to solve for v on your own before you watch the next video.